Let's review some electrical engineering questions, answers, and formulas. We'll begin with circuit analysis. Firstly, consider this question. Find the current through a 10 ohm resistor connected to a 12-volt battery. Using Ohm's law, which states that voltage equals current times resistance, or volts equals amps times ohms, we can solve for the current. Rearranging the formula, current equals voltage divided by resistance, or amps equals volts divided by ohms. Therefore, the current equals 12 volts divided by 10 ohms, which equals 1.2 amps. Secondly, let's calculate the voltage across a 10 microfarad capacitor connected to a 5-volt power supply. The formula for capacitance is capacitance equals charge divided by voltage, or farads equals coulombs divided by volts. If we know the charge, we can calculate the voltage. Assuming the capacitor is fully charged, the voltage across the capacitor will be approximately equal to the voltage of the power supply, which is 5 volts. Thirdly, let's determine the power dissipated by a 100-watt light bulb connected to a 120-volt outlet. We know that power equals voltage times current, or watts equals volts times amps. We also know that voltage equals current times resistance, or volts equals amps times ohms. We can find the current drawn by the light bulb using the power formula. Rearranging it, we get current equals power divided by voltage, or amps equals watts divided by volts. So, the current is 100 watts divided by 120 volts, which is approximately 0.833 amps. Now, let's move on to electrical machines. Firstly, let's describe the principle of operation of a transformer. A transformer works on the principle of mutual induction. It consists of 2 or more coils electrically isolated but magnetically linked. When an alternating current flows through the primary coil, it creates a time-varying magnetic flux. This flux links with the secondary coil, inducing an electromotive force, or voltage, in the secondary coil. The voltage transformation ratio is proportional to the ratio of the number of turns in the primary and secondary coils. Secondly, let's explain the construction and working of a direct current motor. A direct current motor consists of an armature, a field winding, a commutator, and brushes. The armature is a rotating part that carries the current. The field winding creates a magnetic field. The commutator and brushes provide a means of supplying current to the armature windings. When current flows through the armature winding, it interacts with the magnetic field produced by the field winding, creating a torque that causes the armature to rotate. Thirdly, let's calculate the efficiency of an induction motor. The efficiency of an induction motor is defined as the ratio of output power to input power. Efficiency equals output power divided by input power. The output power is the mechanical power developed by the motor, and the input power is the electrical power supplied to the motor. Losses in the motor, such as copper losses, core losses, and friction losses, reduce the efficiency. Now, let's consider power systems. Firstly, we will define power factor and explain its significance. Power factor is the ratio of real power, measured in watts, to apparent power, measured in volt amps. It is a dimensionless number between 0 and 1. Power factor indicates how effectively electrical power is being used. A low power factor means that a large amount of reactive power is flowing in the system, which increases current and losses. Secondly, let's calculate the power transmitted through a 3-phase cable with a line voltage of 13.8 kV and a current of 100 amps. The formula for 3-phase power is power equals the square root of 3 times the line voltage times the line current times the power factor. Assuming a power factor of 1, the power is equal to the square root of 3 times 13,800 volts times 100 amps, which is approximately 2384 kilowatts. Thirdly, let's describe the operation of a synchronous generator. A synchronous generator converts mechanical energy into electrical energy in the form of alternating current. It consists of a rotor with field windings and a stator with armature windings. The rotor is driven by a prime mover, such as a turbine. The field winding is excited with a direct current, which creates a magnetic field. As the rotor rotates, the magnetic field sweeps across the stator windings, inducing a voltage in them. The frequency of the generated voltage is synchronized with the rotational speed of the rotor. Next, we'll talk about control systems. Firstly, let's define the terms open-loop and closed-loop control systems. An open-loop control system is a system where the output is not fed back to the input. The control action is independent of the desired output. A closed-loop control system, also known as a feedback control system, is a system where the output is fed back to the input, creating a feedback loop. The control action is based on the difference between the desired output and the actual output. Secondly, let's explain the function of a proportional integral derivative controller, also known as a PID controller. A PID controller is a control loop feedback mechanism widely used in industrial control systems. It continuously calculates an error value as the difference between a desired set point and a measured process variable. The controller attempts to minimize the error by adjusting the process control inputs. The PID controller involves three separate parameters. Proportional gain determines the response to the current error. Integral gain determines the response to the accumulation of past errors. Derivative gain determines the response to the rate of change of the error. By tuning these three parameters, the PID controller can provide precise and stable control. Thirdly, let's design a block diagram for a temperature control system. A temperature control system typically consists of a temperature sensor, a controller, and a heating or cooling element. The temperature sensor measures the actual temperature and sends a signal to the controller. The controller compares the measured temperature to the desired temperature set point. Based on the difference, the controller sends a signal to the heating or cooling element to adjust the temperature accordingly. The block diagram would show the sensor, controller, and heating or cooling element connected in a feedback loop. Now let's review some essential electrical formulas. Firstly, Ohm's law states that voltage equals current times resistance to volts equals amps times ohms. Secondly, capacitance is defined as charge divided by voltage, or farads equals coulombs divided by volts. Thirdly, power is defined as voltage times current, or watts equals volts times amps. Fourthly, the transformer ratio is defined as the number of turns in the primary winding divided by the number of turns in the secondary winding equals the voltage in the primary winding divided by the voltage in the secondary winding. Fifthly, motor torque is related to motor constants and armature current times field current. Sixthly, power factor is defined as real power divided by apparent power. Seventhly, power transmission can be calculated as voltage times current times cosine theta. Remember that it's important not to solely rely on questions and answers for exam preparation. Make sure to understand the underlying concepts and principles of electrical engineering. Thoroughly study relevant textbooks and materials to ensure a comprehensive understanding.